Carbohydrates can also be a different kind of isomer in the realm of stereoisomers. So remember that stereoisomers is a general term for isomers that have a different arrangement around one particular atom. A type of stereoisomer that we talk about a lot is an enantiomer. So again, I want to be clear, remember that an enantiomer is a special type of stereoisomer. Enantiomers in particular are stereoisomers that are non-superimposable mirror images. This means all you did was rearrange the atoms around one point, and through that rearrangement, made a mirror image. So again, this is an enantiomer. Remember that we can distinguish enantiomers and stereoisomers using a special type of nomenclature. And again, you should have learned about this in organic chemistry, and we did touch on it a little bit when we talked about amino acids as well. Remember, this was in organic chemistry, the R and S type of distinguishing of an isomeric center. And R and S is akin to, in other biological usages, the D and L system. So remember, if you are familiar with R and S, here R is equivalent to D and S is equivalent to L. So for sugars, we will use the D and L nomenclature, which again means that they contain a chiral center that can be distinguished based on the positioning of their atoms around a chiral center. Now remember that enantiomers have physical properties that are generally the same except for their ability to rotate light. In living organisms, our sugars, and in particular our hexoses, those are 6-membered sugars, are mostly D stereoisomers. But there are some simple sugars that we utilize and that exist mostly in the L form. One example is L-arabinose. So again, most sugars that we are going to be talking about and that we utilize are in the D form, the D and stereoisomer, but there are some that do utilize the L form. So here's a visualization of, again, enantiomers. Enantiomers are mirror images of each other. Here's a sugar. Remember, a chiral center is any atom that has 4 different things bound to it. And you can see that we have not changed the position of bonds, right? Things aren't bonded to different things. It's just that the positioning around an atom has changed. And this does somewhat change the properties and the ability of molecules to bind. Chiral compounds can be drawn using different types of perspective formulas. One that you will see for sugars, and again, you might have been introduced to in organic chemistry, is this Fischer projection formula. In this type of formula, we use straight lines instead of lines that represent wedges and dashes. And below in the perspective formula, you can see the 3-dimensionality of what these lines represent. So Fischer projections are a simplification of 3-dimensionality. And what they really mean is that the things that are in the horizontal plane are coming up, so they are wedged up at you. And the things that are in the vertical plane here are going down and away, as shown in these drawings here. Now, to give you an idea to remember generally how to figure out if something is D or L, R or S using a Fischer projection, this is the tip. In particular for sugars, if you always draw the carbon that is your carbonyl carbon at the top. Now remember, this could be a ketone or it could be an aldehyde, but if you keep it at the top and keep the carbonyl carbon here, and the end of sugars usually has a CH2OH like this, if that is on the bottom. If an OH is on the left, it is in the L form. And if an OH is on the right, it is in the D form. Now, we talked about this particular type of stereoisomer, which is an enantiomer. Remember, that is a direct mirror image. And as we saw here, these are the same molecule, but they are enantiomers of each other. So it is glyceraldehyde, but D or L glyceraldehyde. There is another type of stereoisomer. Usually in organic chemistry, we call these diastereomers. Another name for diastereomers when talking about carbohydrates in particular is epimers. So it's the same, it's the exact same concept, it's just a different word, a different name that is used. So epimers are a type of stereoisomer that differ at one chiral center. They're not mirror images, and so they are not enantiomers. And I'll show you an example of this in a second. So they still have the same bonds. All of the atoms are bonded to each other in the same way. The arrangement around a chiral center has been changed. So just two things have been flip-flopped and arranged slightly different. Atoms are just arranged differently. But in this case, they're arranged in a way that makes them still have the same chemical formula. They are still stereoisomers, but for epimers, they are not enantiomers. Let's look at an example of this. So again, here we have a couple different sugars, and let's talk about how they're related to each other as isomers, or maybe not isomers. These are all aldoses. They have a carbonyl that is an aldehyde at the top. The one on the bottom, or on the left, is the particular sugar we were looking at earlier, which is glyceraldehyde. It has 3 carbons in it. So it is a aldotriose, right? Now, erythrose and threose, which are aldoses that have 4 carbons in them, have the same chemical formula. There's an aldehyde here. You can see there's 1, 2, 3 more carbons, total of 4. They both have this CH2OH group at the bottom. They both have an OH bound to a carbon here, but notice it's just on a different side. Similarly, at this point, they have an OH bound to that carbon, but on a different side. So again, the definition of an epimer is that one stereocenter, one of many, there are 2 stereocenters here, 2 places where we have a carbon that is bound to 4 different things. So there are 2 stereocenters. One of them has been changed, right? This one, the OH is on the left instead of on the right. Now, this bottom stereocenter, this bottom area, the OH is on the same side. So there's no change that has happened here. This is clearly a stereoisomer. Again, it fits all of the key points, has the same chemical formula. All of the bonds, everything is attached in the same way, except that we have just rotated our groups around the same atom. And this is an epimer in that it is not a mirror image, right? This erythrose does not reflect to equal three rose. It is a stereoisomer, though. There are lots of epimers in our sugar chemistry and carbohydrate chemistry. So, for example, mannose and galactose are just epimers of glucose. These are 3 different sugars. They all have very different properties, but they really are only 1 bond rotation different from each other. They're all diastereomers of each other. None of them are mirror images of each other. None of them are enantiomers, but they do all have the same chemical formula with just 1 different rotation around a carbon bond. So you can see mannose, for example, this carbon number 2 is the one that has changed when compared to glucose. You can see it was previously on the right in glucose, and it is now on the left for mannose. But all the other OH groups are the same. Similarly, galactose, its only difference is at carbon number 4. In glucose, the OH group is on the right, and in galactose, the OH group is on the left. Notice that none of the other centers, when comparing each other, are changed, so they are epimers in relation to glucose. So, for example, galactose and glucose are epimers of each other. There is only 1 difference between glucose and galactose. Mannose and glucose are epimers of each other. There's only 1 rotation difference between mannose and glucose. Now, what about galactose compared to mannose? There are more than 1 changes when comparing mannose to galactose. You can see that galactose's carbon number 2 and its carbon number 4 are different than mannose's carbon number 2 and carbon number 4. When comparing galactose to mannose, these are still stereoisomers and they are diastereomers, but they are not epimers. Only because epimer means that there has to only be 1 distinguishable change.